Hey, Pre-Calc students, this is going to be our next lesson in functions about combining transformations. So at this point, we know how to translate functions, shift them left, right, up, down. We know how to do reflections. We know how to do dilations. So now what we're going to talk about is let's put all those pieces together and start moving the graph left, right, up, down, flipping it, and then also stretching it. Okay, so taking a look at some quick recap information. This is all the stuff we should now know already, okay? So we've got some left-right information here. If we have f of x minus h, it's going to move the graph to the right. F of x plus h, we saw moves the graph to the left. Some very colorful notes coming your way today, by the way. Taking a look at a times f of x. If we're multiplying by a scale factor on the outside, if the scale factor is bigger than 1, we have a vertical dilation, and this would stretch the graph. If the number that we multiply is between 0 and 1, according to our prior lesson, that's going to shrink the graph vertically. Now, there is such thing as a horizontal stretch or shrink, but we're not going to look at that in this unit. It is something that you would have learned last year in Algebra 2. Some other things that we now know, we know how to move the graph up and down if we add or subtract k on the outside of the function, and that follows the same sign, right? Whereas if I see x minus h, we should be moving to the right. F of x plus h goes left. Here, plus k does move up, minus k moves down. And then finally, the effect of having a negative sign is going to be a reflection over one of the axes. When you're negating the outside of the function, it flips over x. When you negate the inside of the function, it flips over the y-axis. Okay? So I'm going to show you a pretty methodical way that we're going to break down these transformations if there's more than one applied to the same function at once. So order of operations really does matter here. We can't just say, yeah, you know, I think I like to move it up, down first, and then I'll maybe shrink it and then flip it and then go right. I mean, you can't necessarily just go in whatever order you think looks best. There is an order and a method to the madness here. And it happens to follow essentially PEMDAS. But I'll tell you, PEMDAS for us kind of shifts into something slightly different when we're talking about transformations. So if we have, first and foremost, what we have to do is we have to think about the horizontal shift right here. So does it go left, right at all? We have to do that first. The next thing we do is we consider any reflections. Are there any negatives? Am I reflecting over the x-axis or the y-axis? That would happen next. Okay. After that, you're going to ask yourself, is there any dilations happening? Dilations would be multiplying by some sort of scale factor a. And then the last part is considering, do we have any vertical shifting happening? So instead of doing PEMDAS, when we sketch transformations on functions, the acronym HRDB is what I see students write a lot on their papers, because I think Algebra 2 teachers use this a lot. So it's horizontal, reflect, dilate, vertical shift. And if you didn't have a teacher that used this last year, not a big deal. Maybe I'll convert you this year into using these 4 steps. But, you know, think of a phrase that you kind of like that helps you remember this order. Like, I'm not really sure why I've heard this phrase a lot, but I've heard like, Harry really does vacuum. I don't know. Maybe I'll give a bonus point to whoever comes up with a better one than that. Harry really does vacuum. I mean, I guess it's okay, but I feel like you guys can do a better job than that. Get back to me if you come up with a better acronym for HRDB. Here's the first example we're going to look at. Y equals -2 times the quantity x minus 1 squared plus 3. You know, we might as well right out the gate try something that has a little bit of everything mixed in. And I'll show you what the approach is going to look like for something like this. Before we even get started in identifying what type of transformations are happening, I'm going to ask you in every case today to identify the parent function. Like which function that we know a lot about is being transformed in some way, shape, or form. And when you have this quantity squared, I'm hoping that you would say it's the function y equals x squared. Because we know a lot about y equals x squared. We know it's a parabola. We know the vertex is at the origin. And we know all those good things. So in fact, maybe off to the side here, I'll create a quick set of axes. And just say, you know what, for the parent function, let's make a quick table of values, and then we'll see what that graph looks like. So for my parent, I think a decent table of values to use for this parent is -2 to 2. Right? We get a little bit of the left side of the parabola, a little bit of the right side. The outputs when I square those values of x would be 4, 1, 0, 1, 4. So if you go ahead and plot those, the only thing that I like to do for the parent is you don't necessarily have to sketch the parent. I like to compare it to what the end graph looks like anyway. But I usually make it a dotted line so that this way we don't confuse it with what the final product should look like. All right, let's kind of start thinking about then what are the transformations that have to happen to the parent function y equals x squared. Remember, this is the order we're going to go in. Horizontal, reflect, dilate, vertical shift. So let's talk about our transformations. And we'll make a quick list here. Okay, so number one, do we have a horizontal shift? And the answer is, yeah, we have to go to the right one. So we're going to move this whole thing to the right one, according to the x minus 1 on the inside there. And the other thing I'm going to do is once I write down the transformations, I'm going to write down next to it what values get affected by this. If I take this whole graph and I move it to the right one unit, that's going to take all the x values and add 1 to them. And why do I write this down? Because it's going to help me figure out like what's a new table of values for the transformed function. Okay. All right, step number 2, is there a reflection? Well, if I see a negative sign anywhere, yep, there it is. There is a reflection. And if the negative's on the outside of the function, we saw that it's a reflection over the x-axis. So we are going to next reflect over x. Now, even though you're reflecting over the x-axis, I want you to keep in mind that that's negating the y. Right? If you take a value and you flip it over the x-axis, a positive y becomes a negative y. So that's the operation that's happening when you reflect over the x-axis. Okay. Number 3, is there a dilation? And the answer is, yeah, there's a number being multiplied on the outside. So we're going to dilate by a scale factor of 2. This is a vertical stretch. Okay, so if you want to write it as vertical stretch, that would be okay. Just something indicating, yep, we have a dilation, and the scale factor of that dilation is 2. Since this is a vertical stretch, that's going to double the y values. And any dilation we have will always affect the y values. Okay, so actually, let me write that in. It's a vertical dilation. What you'll notice is that these 2 steps could actually probably be accomplished at once. If I negate y and then I double it, that's the same thing as multiplying y by -2. So to simplify our process a little bit, when I come up to this table, I'm actually just going to multiply my y values by -2. And then finally, the v part, is there a vertical shift associated with this transformation? The answer is yes. We've got to take the whole graph and move it up 3. So because of that last part here, moving it up 3, what does that affect? That it'll also affect the y values. We're going to take all the y values and add 3. So here's the list of what I have to do to the table that we made for the parent function. So let's come back up here for a second and say, all right, now we're going to transform this graph according to the rules that we just outlined in this transformations list. Now, if I look at the list quickly, the only thing that affected the x values is adding 1. We're moving it to the right one. So I'm going to just take my x list real quick and add 1 to everything. So now it should be -1, 0, 1, 2, 3. So that was kind of a quick and easy fix. I have a little bit more to think about with the y values, and you have to do it in this order. Make sure you multiply by -2 and then add 3 to the y values. So that would be, let's see, -8 if I multiply that by -2. Plus 3 would be -5. And then this would be -2 plus 3 is 1. This is going to be 0 plus 3 is 3. And then we should see things repeat, right? Because if I do -2 times 1, that's -2. Plus 3 is back to 1. And then finally, this would be -5 here. All right, this is the table of the transform function right up here above it. So if I plot those 5 points, I am done. I have sketched successfully this function right here without the use of a calculator. That's the whole goal, by the way, of course, right? To be able to sketch this without a calculator. So if I plot -1, 1, 2, 3, 4, 5, we've got 0, 1, 1, 1, 2, 3. I'm just going to come back down on this side. Okay, take those 5 points, connect them with the parabola. in the end, it should look like your graph got moved to the right 1 unit. It flipped over the x-axis. It got stretched, and then it got moved up 3. And you can kind of picture each of those things happening. Right 1, flip it, stretch it, move it up. And there's my final graph there. Okay. So this is how we're going to do our approach today. Every time I give you an example, we're going to think about, hey, what's the parent function? Let's make a table for it. I want you to list the transformations and apply those transformations to the table of values that we've created. Okay, let's get right into another practice problem here. So if we have in number 2, y equals 2 times the square root of negative x plus 1. All right, the parent function this time, I'm hoping you're saying to yourself, is not x squared anymore, but how about just y equals, the square root of x. Okay, so if that's the parent function, y equals the square root of x, my table that I create is going to look a little bit different. Mostly because I don't want to start with x equals -2. The square root of -2 is not a real number. So it doesn't make sense to go from -2 to 2 in your x list for the parent function y equals the square root of x. Why don't we in this case go like 0, 1, 4, 9? And those shouldn't look like a random set of x values. Those should be really smart x values for us to choose, because these are all a list of perfect squares, aren't they? So then if I take the square root of all those values, square root of 0 is 0. This is 1, 2, and 3. All right, so in a second, we can go ahead and plot that parent function. I might even skip 9, 3, because that seems like it's going to be a little bit off the grid there. Not a huge deal, but if I go ahead and make a set of axes, you've got 0, 0, 1, 1, 4, 2. And if you guys have room to plot 9, 3, go for it. But I know the parent function looks like this for radical x. Okay, so then let's talk about our list of transformations. If I were to transform this according to the rules up above, step 1 would be, if we do HRDV, is there any horizontal dilation? And the horizontal translation, we're not shifting left or right at all, right? There's no x plus or x minus underneath the radical. So there's no horizontal shift to start. If you almost think of like writing this down, guys, there's no h. Okay, there is a reflection though. I see a negative there, and when you directly negate x, that's going to flip it over the y-axis. So this graph will reflect over y. But to reflect over the y-axis, you're doing exactly what's indicated there. You're negating the x values. Okay, so we'll do that in just a moment. Okay, is there a dilation? The answer is yes. We still have that scale factor out front again. So there's a vertical stretch by a scale factor of 2. Remember, since these are always vertical stretches in our notes today, we're going to have 2y is the result of that. And then finally, the last part, is there a vertical shift for HRDV? The answer is yes. The entire graph will move up 1. So when you do that vertical shift in the last step, that will affect the y values, and we're going to add 1 to the y's. Okay, so let's come back to the table then and say, after all those transformations, what is this going to look like? Okay, so the first thing I'm going to do is I'm going to take my list of x values and negate them. That's the only thing that's happening to x. So it'd be 0, -1, -4, -9. Then we're going to double the y values and add 1. So 0 times 2 is 2, plus 1 is 1. 1 times 2 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. 3 times 2 is 6, plus 1 is 7. And again, I might even ignore the last point, -9, 7. I think I kind of get what's going on here. But here's the point 0, 1. Here's the point -1, 3. And then we've got -4, 1, 2, 3, 4, 5. So you can see a couple things are going to happen here when I connect these points. Okay. Certainly as compared to the original, it did get flipped over the y-axis. It got stretched by that scale factor 2, and the whole graph moved up 1. And once you make that sketch, kind of run down that list real quick in your head and make sure that the graph confirms each of those scenarios there. All right, I'm going to recommend that you try the next one on your own now that you've seen two, and hopefully this looks familiar from last year anyway. I would say once you write this down, hit pause and give it a try, but I'm going to go over the transformations for this one in just a moment, okay? Think about the parent function. Parent function this time is absolute value of x. So I would say at this point, hit pause, give it a shot, and then once you're done, we'll go ahead and double check sketches here, all right? All right, so for the parent function, the table that I would choose is -2 to 2 again, just like I did for quadratics. Because when I do those outputs, we get 2, 1, 0, 1, 2, right? Absolute value takes something and makes it positive. So if I think about the parent function, okay, the parent function is going to look something like this, that V shape that we know absolute value looks like. All right, so let's talk about our list of transformations. Do we have H? Do we have a horizontal shift? The answer to that is yes, we do have a horizontal shift. So my list of steps here would be shift to the right 2, which is going to move my x values +2. Then we have to think about reflections. Yep, there is a negative on the outside, so we're going to reflect over the x-axis, which remember means negate y. Is there a dilation? Yes, there is a 3 out front, so we've got a vertical stretch of 3, which is going to triple the y's. Remember what we saw earlier is that you can do those in combination with each other. You can actually just take the y's, multiply them by -3. And then the last step is to move everything up 5. There is a vertical translation there. So we're going to have y + 5 there. And I went through that list pretty quickly, but hopefully after 2 examples, you're kind of getting the idea here of what's happening. And notice how really there's typically only one thing that affects the x values, and I think that will be pretty common for us, if anything. So if we move to the right 2, this is now an x value at 0, and then everything else would go up 1 from there. So we're now at 0 through 4 in my x list, and y multiply it by -3 and add 1. So this would be -6, or add 5, sorry, -6, and then +5 is -1. And then 1 times -3 is -3, +5 is 2. This is going to be 0 + 5, which is 5. And then the nice thing is, just like with the parabola, it repeats on the other side of the vertex. Okay, and the vertex in this case is right in the middle at 2, 5. So if I plot these points, we get 0, -1, 1, 2, 2, 1, 2, 3, 4, 5. And then on the other side of the vertex, we get 3, 2, or -1. Okay, so that's what that graph would look like then. Right? So we took the absolute value, we shifted it to the right 2, and then we flipped it over, stretched it, and moved it up 5. All right, so hopefully that's a good starter point here for us to get some more practice with this concept in class tomorrow. The last thing I want to talk about quickly is thinking about what the difference is when you have the function y equals x² minus 4, and what would happen if I put absolute value around that function. Okay, so this is not a traditional reflection, dilation, translation. Okay, there is some transforming that's going to happen to this graph, but it's not a straight up single rule that applies. So here's what we're going to do. If I think about x² minus 4, what I want you to be thinking about here is that this is a parent function x² that got moved down 4 units. And if I take, the parent function and I move the other points down 4 units, you wind up getting a sketch that looks something like this. Okay, so there's y equals x² minus 4. So I want you to think about, now when I put absolute value bars around that, how does that change the appearance of this graph over here, right? So it is some sort of transformation, but it's not a direct, let's move it here, let's flip it there, okay? Think about what happens when you input to this function, the outputs for y, because of the absolute value here, are only positive. So what I'll have you think about is, let's think about what's happening around the points where we hit 0. To the left and right of 0, the original graph was positive, wasn't it? right? Here it's positive and here it's positive. It's above the x-axis. So when I do absolute value of those positive numbers, they're going to stay positive. Okay, those two parts of the graph are identical. But anything below the x-axis right now, where the entire graph is negative, when I take the absolute value of all those negative y values, they're going to become positive y values. So now actually that part at -4 flips up to +4, right? I mean, plug in 0. 0 squared minus 4 is -4. Absolute value of -4 is +4. So that whole part actually flips up. You get like a W-shaped graph now. So what does absolute value do? It takes any part of the graph that's negative, meaning below the x-axis, and flips it above. So it doesn't flip the entire graph over, right? These parts stayed in place, but anything that's negative gets flipped up. And we'll talk about this idea a little bit more next time I see you in class. I think there's some practice in the packet that we'll look at. All right, that's it for today's lesson on combining transformations. We'll do more practice next time I see you.